Hello, welcome to the second part of the DANTE Press Quench model series. In this video, I will be showing you how to build a press quench model by creating the die geometries and applying contact interactions between the ring slice and the dies. At the end of this video, we can go through some of the results and see the effects that the die has on the stress and deformation of the part. Before we get started with the stress model, if you haven't already, please open up the Press Quench CAE file from the previous video. Once we have the CAE file open, inside our model tree, we should see a press quench _T for the press quench thermal model that we built previously. Once we have this open in our model tree, we can go to Plugins, DANTE Model Builder, make sure our active model is press quench _T and thermal, and click Convert to Stress. Once we've converted the model to a stress model, inside our model tree, we should see a new model appear called press quench _TS. This should have taken us to the mesh module. Inside the mesh module, we're going to select mesh, element type, box select the entire part, click done, and change this from a heat transfer element to 3D element for stress. Once we've selected 3D stress, we can uncheck reduce integration and click OK. Now that we changed the element type to 3D stress, the next step is to build our die parts. To do that, we can go back to the part module, click create part, and the first part we're going to build is the top die. For the top die, we want to make sure the modeling space is set to 3D. Instead of deformable, the 3D die will be a discrete rigid type. For shape, we're going to use shell and select revolution. To create the geometry, we're going to select the create lines option here, and I'm going to be giving 4 coordinates for the 4 corners of the die. The first coordinate will be 2751. The next coordinate will be 2750, and these coordinates will make a little bit more sense once I actually generate the part. The third coordinate will be 4850, and lastly, the fourth coordinate will be 4851. So once we have those 4 points created, we don't actually have to close off the box because this will be a shell type geometry. So we can deselect create lines here, click done, and for the angle, we're going to use an angle of 5 degrees like we use for the ring slice in the thermal model. So we can click OK, and this is our top die created. Next, we're going to be creating the bottom die piece. Using the same settings here, we can just click continue. And the geometry, we're going to use create lines, and for the geometry, the first coordinate will be 27 -1, 27 0, 48 0, and 48 -1. Again, we don't have to close out this box here. We can deselect create lines, click done, and just click OK to generate our bottom die geometry. Lastly, let's create our expander part. For the expander, the first coordinate will be 24 2, 25 2, 25 48, and 24 48. Let's deselect create lines, click done, and click OK here to generate our expander part. So once I have the 3 pieces created, the next thing we're going to do is create a reference point for each of these pieces. The reference point would be used to apply the load and the displacement boundary conditions for these rigid bodies. To create the reference point, inside our part module, we're going to go to Tools, Reference Point, and select one of the yellow points here on the surface of the part. Once we created the reference point, it should pop up inside our part here, and if we go inside our model tree, expand part, go inside expander here, go to features, we should see the reference point pop up. I'm going to rename this to something a little bit more descriptive, so I'm going to call this expander RP, and we're going to do the same thing for the top and bottom die now. So let's change the part to bottom die, go to Tools, Reference Point, select any point on the surface here, go inside our bottom die and rename this to bottom die RP. Lastly, let's do the same for our top die. Tools, reference point, and change the name inside our model tree here. Now that we created the reference points for our three pieces that we just created, let's go to assembly and create an instance of the bottom die, expander, and top die. If you use the same coordinates to define the top die, bottom die, and expander, it should be perfectly touching our ring slice here with no separation between the surfaces. So this would make convergence a little easier and help make it easier to set up the model. So now that we created the instance and added it to our assembly, we can go to the mesh module here, select part, and mesh each part individually. To keep it simple, all we have to do is go to seed part and change the global size to 0.75 here. Click apply, click OK, and just mesh the part this way. So this will be our mesh for the top die. Next, let's move on to the bottom die here. Click seed part, and we can use the same value. Click mesh part, and mesh the part here. The last part will be the expander. Let's go to seed part, and again, we can just use a value of 0.75. Click OK, and mesh the expander. Now that we created the mesh for each of the parts, we can go back to the assembly module and define our different sets that we will need in order to apply the boundary conditions and contact interactions. So if we go to Tools, Set Manager, the first set that we're going to create is an inner node set on the inner surface of on the two inner surfaces of the ring slice. So this will be used to fix the ring slice in the circumferential direction in the assembly. So to make it a little bit easier to select the inner nodes, if we go to assembly inside our model tree here, we can expand instances and select the three parts that we just created. If we right click, we can click hide to hide the three parts inside our assembly. This way, when I go to create, select nodes, we can easily select the inner nodes on the surface here without accidentally selecting a node on the top, bottom, or expander piece. To select the inner nodes on the ring slice, instead of individually, we can change this option to by angle, and we can leave this as 20 degrees. So now if we select a node on the inner surface here, it will automatically select all the nodes within 20 degrees of that node. Next, if we rotate the camera, hold shift and select all the nodes on the other surface, we can click done. So that's our inner nodes defined. Next, if we unhide the die pieces, we have to create a nodal set for each of the reference points. So the top die reference point, expander, and bottom die reference point. So the first set I'm going to create is the top die reference point. We can leave this as geometry, click continue, zoom in a little bit, and select the top die reference point. Next, let's create the expander reference point. And select the bottom die reference point. So those are all the nodes that we will need to define for this model here. So if we have those four new nodal sets defined, we can dismiss and define our contact surfaces now. So we can go back to Tools, Surface, Manager here. And for the surface sets, we're going to define the contact surfaces between the die and the ring slice. So the top surface here the ID surface of the part, and the bottom surface of the part. So first things first, again, we can hide the die geometries here. Go to create. The first surface I'm going to create is the ring top surface. We can select the top surface of the ring and click done. Next will be the ring ID surface. Rotate the camera and select the ID surface here. Lastly, let's select the ring bottom surface. Rotate the camera and select the bottom surface of the ring. Now that we have those surfaces defined, we have to define the surfaces for the bottom die, expander, and top die now. So if we unhide those parts and hide the ring slice, we can use the same method to define the die surfaces. So if we go to create, I'm going to call this top die surface and select the surface of the top die. So if I click done here, it's going to ask us for an extra option, so brown or purple. This is just if we want to select the top surface of the die or the bottom surface of the die, since these are shell geometries, shell parts. Since the contact will be on the inner surface of the top die, we can select brown here. So next, let's define our expander surface. And similarly, if we select the surface here, it's going to ask us to choose either brown or purple. And again, we want to select the inner surface of the expander piece, so we can select brown. Lastly is the bottom die surface. This time the inner surface is purple, so we can click the purple option. So those are our surfaces that we have to define. So with those defined, we can close out of the surface manager here and unhide the ring slice. Lastly, before we move on to applying the load and boundary conditions, we have to create a cylindrical coordinate system so that we can fix the part or the ring slice in the circumferential direction here, and not just since the global coordinates wouldn't be able to fix it properly. So to create the cylindrical coordinate system, we can go to Tools, Datum, and select the CSYS option for coordinate system. So inside here, we can select the 3 points method. I will call this CYL for cylindrical, and select the cylindrical option. The first question it's going to ask us is the point of origin. Since this part is revolved around the 0, 0, 0 axis, so the origin of the origin here, we can leave this as 0, 0, 0 and click enter. Next will be the R axis. So this is the radial axis that we will have to define. So the radial axis here will be along the x direction of the part, so going this way. To define that, we can just give a coordinate of 1, 0, 0 and click enter. Lastly is the R theta plane, or the tangential or circumferential plane here. Right now it's defined in the vertical direction. We want this to be pointing in the z direction, so this way, circumferential to the part. So to define that, we can give the coordinate of 0, 0, 1. So that's our new datum coordinate system created. So we can close out of this window, close out of the create datum window, and if we go inside our assembly here and expand features, we should see our new coordinate system CYL here. So if I hide this and take a look at the coordinate system, you'll notice that our R is pointed in the x direction, which is correct, which is what we defined, and our T or tangential is pointed in the z direction, circumferential to the part. So if we unhide this, next we can apply our displacement boundary conditions to the part and to the dies. So to do that, we can go to the load module here and open up the boundary condition manager. So the first boundary condition we're going to add is for the circumferential direction of the ring slice. So we can go to create, and for the name, I'm going to call this circumferential fixed. This will be applied to the initial step here, and we're going to use the displacement / rotation boundary condition. So now it's going to ask us to select the node set here. So we can go to sets and select the inner nodes that we defined. For the coordinate system, instead of global, if we click the arrow here, we can choose the cylindrical coordinate system that we just created. For the cylindrical coordinate system, U1 instead of x refers to the radial direction now. U2 refers to the tangential direction, and U3 refers to the axial direction, or the z direction of the cylindrical coordinate system. So since we just want to fix this in the circumferential direction, all we have to do is check U2 here and click OK. So that's our circumferential direction fixed. Next, we can fix each die part individually. So first, if we go to create again, we can fix the top die now. So top die fixed. We can click continue. Select the top die reference point. And for the top die, we want to fix this in all directions except for the vertical direction here, or the Y direction. So to fix in all the directions but the Y direction, we can select U1 for X, U3 for Z, and all the rotational directions too. Next, let's create our expander boundary condition. Select the expander reference point. And for the expander, we want to fix this in all the directions but the radial direction, or the X direction. So to do that, we can check U2 for Y, fix it in the U3 direction for Z, and all the rotational directions. Lastly, let's fix our bottom die. Select our bottom die reference point. And for the bottom die, we want this piece just to be fixed in every single direction. So if we have the 4 different boundary conditions created, we can close out of this window. And now we can apply our loads. For the loads, we can go to Load here up at the top, click Manager, and this will open up the Load Manager menu. The loads that we're going to be applying will be to the expander reference point and the top die reference point. So to do that, the first thing we're going to do is click Create. And I'm going to be defining the load for the top die first. For a load, it has to be applied to any step, or not the initial step here. So let's select Heating, Mechanical, Concentrated Force, and we can click Continue. Again, for the node set, we can select the top die reference point, and this should pop up the Edit Load window. Since we defined it in the heating step first, and we want to apply the load in the vertical direction, we can give the X direction CF1 0, and the Z direction 0 also. For the CF2 direction, the Y direction, we want this to be going down. We want to apply a load in the negative direction here, going downwards, so we can give this a load of -1. And click OK. So this created the load of the top die in the heating step, and will propagate to all the steps now. The reason we gave a load of -1 in the heating step is so that we can fix the ring slice in the vertical direction without having to fix a specific node in the ring slice in the vertical direction. Using -1 won't affect the actual stress or deformation results, but will be enough to fix the part in the vertical direction, so that we can constrain the ring slice properly inside the assembly. Now, if we go to Edit, or if we select a step, not the heating step here, and click Edit, you'll notice that our force of -1 is propagated through all of the steps here. To change the load, all we have to do is select a specific step that we want to change the load value in, click Edit, and change the value here from -1 to a value of 200. So now, in each of the following steps, the value should be -200 now, as we can see. And during the remove load step, we can remove the load of 200, and change this back to 1 so that we can fix the part in the vertical direction without actually affecting the stress or distortion results. Next, let's create our load for our expander piece. Similarly to the top die load, we can select heating as the first step here and click continue. We'll select our expander reference point, and instead of in the Y direction this time, we're going to be giving a load in the X direction, or the radial direction. So CF1 will give a load of 1, 0, 0, and click OK. So again, we'll have to edit the add load step and the remove load step for the expander load. So in the add load step, we can click edit and change this from 1 to 200 to apply the expander load to the part during this step. And during the remove load step, we can edit and change this back to 1 to remove the load. So now that we have those two loads created, we can dismiss and close out of the load manager window. And let's save the model before we move on. The last thing we have to do for the press quench contact model is to define our contact surfaces here. So to do that, inside our module, we can go to interactions, click interaction here up at the top, click manager, and click create. So the first interaction we're going to create is our top die contact interaction with the ring slice here. So I'm going to call this top die ring int for interaction. Select initial as the step because we want the contact to be applied right at the beginning of the model. We can use surface to surface contact here and click continue. The first surface that we're going to be selecting is the main surface. So for the main surface, we can select the top die surface here and click continue. And the second surface will be the secondary type, so the secondary surface here, which we can select the top surface of the ring slice. So ring top surface. So the main surface typically is your rigid body surface, which is the top die part, and your secondary surface, Abaqus typically wants you to select the deformable body, which will be the ring top surface here. We can leave these options as default and make sure no adjustment is selected here, since there is no gap between the top die and the ring slice. Lastly, we have to define a contact interaction property here down below. So to do that, we can click create interaction property, and I will call this contact int property. If we click continue, for any contact model, we're going to have to define two contact properties here. So the tangential behavior and the normal behavior. So for tangential, Abaqus gives you many options here. So frictionless, penalty, rough, if you want to model the friction between the surfaces. For this particular model, we can leave this as frictionless and move on to the normal behavior. So for the normal behavior, by default, the pressure overclosure option is set to hard contact, and the constraint enforcement method is default. We can leave these two options as default, and in case you have convergence issues inside your part between the surfaces that you defined, you can play around with these different options here to help with the convergence of the model. For now, we can just leave this as default and click OK, and that's our settings defined for our contact between the top die and ring slice. So we can click OK now and create our contact interaction between the expander next. So again, we can use surface to surface contact, click continue, and select the expander surface here as the main surface and the ring slice as the secondary surface here, so ring ID surface. Since we defined a contact interaction property in the previous interactions, we can use that same setting and click OK. Lastly, let's create our interaction property for the bottom piece. Select the bottom die surface as the main surface and the ring bottom surface as the secondary surface here. Again, we can leave these settings as default and use the contact interaction property that we defined previously and click OK. So those are our three contact interactions defined. So we can dismiss and close out of that window. And now we can open up the DANTE model builder. With the DANTE model builder open, let's make sure we're set to our stress model for our active model. Let's save our CAE file and submit the job. So if our model was successfully submitted, down here it should say it's done with pre-processing. If we give this a second. Let's open up our working directory here. If we scroll down to our stress model, so our LCK file is still here, so it's still analyzing the input file and writing out the parameters. So if we can give this a second. So this stress model, since we have contact properties, should take a little bit longer than our thermal model in our previous video. If we open up our DAT file here to take a look, this is where it does the pre-processing. So you'll see the element type, the different surfaces. So this is the information that the solver will take in order to solve our model. So here it's searching for the temperature that we imported from the thermal model. And if we reload and scroll down, so our pre-processing is done, and now our STA file has been generated inside our working directory. So if we go back to our folder here, scroll down, let's take a look at the STA file. So the STA file for DANTE stress model will output the displacement at the specific degree of freedom monitor that you, or the monitor node that you specified inside your model. Since we're still early on in step 1, before any thermal expansion effects or phase transformations, our displacement should be very small here. Now that our stress model finished running, if you guys haven't already, you can load in the ODB file from the stress press quench model. And what we're going to do is take a look at the temperature first. And this is just to double check whether our temperature history was loaded in correctly from our thermal model. So to do that, up here in the variables drop-down menu, we can select NT11 and go to the very beginning of the process. So before I go through the increments, what I can do first is remove the top die, bottom die, and expander from our contour plot. To do that, I'm going to go to Tools, Display Group Manager, Create. So I'm going to create a new display group that only includes the ring slice here from part instances. So I can click Replace and save this display group and call it ring slice. So now I can look at the temperature profile of just the ring slice without the bottom, top, or expander die, since we didn't apply any heat transfer or temperature boundary conditions to it. So from the very beginning of the heating step, we have a uniform temperature of 20 degrees, which is the initial temperature we defined. If we go through the heating step here and just get to the end, our part should be a uniform or approximately 950 degrees ambient temperature, which is the ambient temperature we defined. So next is the add load step. So this step here, simulating the part going from the oil quench tank or from the furnace to the oil quench press equipment, we will have a slight decrease in temperature here. And after the add load step is our press quench step. So this is where our temperature will start to drop drastically to the 50 degrees ambient temperature we defined to simulate the quench tank. So if we skip to the very end here, our temperature will be around 50 degrees, which is the ambient temperature we defined. So everything looks correct so far. And if we go on to the remove load step here, the remove load step, we use the same ambient temperature and HTC as we did in the previous step, so we shouldn't see much of a difference to the legend or contour plot. So end the remove load step, and last but not least is our air cool step. So our air cool, our part decreases back to room temperature or 20 degrees, and if we go to the very end, we'll notice a uniform 20 degrees for our part. So everything looks to be correct. So next, what I can do is click all here and plot. So this will add back the top die, bottom die, and expander piece, and we can take a look at the stress results. For the stress results, let's take a look at the S11 direction. So this is the stress in the X direction here, the normal stress, or the radial direction here. If we zoom in a little bit here, just to look at the top half, we'll notice a slight compression here on the surface here of about 445 or 443 megapascals. A little bit below the surface here, we have about tension of about 208 megapascals here, which is positive, which represents tension, and negative, which represents compression. So this is the stress in the radial direction. If we move on to the S22, this is the stress in the axial direction, the Y direction here. And we notice a similar pattern here. So compression on the surface and tension closer to the core of the material. So on the surface here, we have a tension, or a compression, of about 448 or 449 megapascals. And as we go closer to the core, we have a tension of about 179 or 180 megapascals. Last but not least, we can take a look at the stress in the Z direction. So this is the stress in the Z direction of the global coordinate system, and technically not the circumferential stress for the cylindrical coordinate system. If we want to transform the results to the cylindrical coordinate system, what we can do is up here at the top, we can click Result, Options, select Transformation, select User Specified, and select the cylindrical coordinate system we defined in our assembly module when we were building our model. So here we can just click Apply, and this will transform the stress to our cylindrical coordinate system. For the cylindrical coordinate system, the S through 3 direction is actually not the circumferential, but in fact the axial or the Y direction here. So to look at the circumferential direction, we would have to change this to the S22 direction here. So circumferentially, again, we have compression here on the surface here, especially at the corners of the part. The compression is about 594 megapascals according to the model, and near the core of the part, we have about 256 megapascals of tension. Since this is such a small ring slice model, if we compare the cylindrical and global coordinate system, so let me create a new viewport here and change this to S33 and change this back to the global coordinate system. The results mapped to the cylindrical versus the global should almost be identical for any direction we were trying to compare. So in this case, the circumferential direction, if we take a look at just the legend are identical between the two results. And that's because for the 3D model, we just use the 5-degree slice. If you use the slice that's a little bit larger, you might have to be careful when you use the global coordinate system to look at the results. So next, let me close out of this viewport here and change this back to the global coordinate system. So now we can look at the distortion. So we can go back to the variables here, scroll down to U, and take a look at the X direction here, or the radial direction. So if I flip this around and take a look at the radial distortion at the end of the process, you'll notice we have a little bit of growth radially, especially here at the top left and bottom left corners here. So there's a little bit of separation between the die and the ring slice at the end of the process here, of about 0.119 millimeters. And if we take a look at the U2 direction now, we'll notice a similar effect of separation between the top die and ring slice, as well as the bottom die and the ring slice here. One cool thing that I can show you is the effect of removing the load after the press quench step. So if I go back to the beginning of the remove load step here, so right before we remove the load back to 1 Newton, and we move the part. So if I scroll through here, you'll notice a slight increase in the deformation in the vertical direction, in the Y direction here. So if we go back to the beginning, right now our displacement is at 0.068, and if I go through the steps, go through the increment, you'll notice this start to decrease and it will grow in the vertical direction, and that's due to the spring back effect of the part as we release the load in the remove load step. So that concludes the Dante press quench stress model video tutorial. Thank you for watching the video. If you have any questions, you can either visit our website at www.dante-solutions.com or email us at support@dante-solutions.com. Thank you.